Okay, so in the previous two lectures, so just to recap what happened. So I started actually giving you, in some sense, the answer to a particular problem, but the advantage was that this answer is extremely concrete and extremely computable. So we learned by playing with usual calculus some symmetries of graphs, which again was brief introduction, if you wish, to three manifolds, because they can be labeled by graphs or four manifolds. So we kind of learned this 3D Kirby calculus from concrete results. And advantage of that is that if you're a mathematician and you want to explore the structure of this invariance, basically table 1, table 2, and table 3 are actually quite interesting invariants. So they have a lot of structure, and many of them are kind of on a cutting edge, so they give you opportunity to study, say, mock modular properties of this Q-series in the last example, or structure of the somewhat untraditional Trans-Simons partition function in table 1. So therefore, if I were to summarize it, I would say that first lecture was actually not really about calculus, it was about Kirby calculus, so that's where topology comes in. So second lecture, I spent pretty much all my time talking about physics, and the goal was to clarify why all these three different tables of integrals have exactly the same symmetries, that it's not really an accident that it has physical origin, and my goal was to explain the physical origin, so we were talking about physics. And today, I plan to spend pretty much entire lecture on algebra, or representation theory. So the subject of this meeting is quantum fields, geometry, and representation theory. So quantum fields is here, geometry is here, and representation theory or algebra is going to be here today in the third lecture. So I want to put this in front of you, this diagram, which again, hopefully familiar from different perspectives to physics and physicists and mathematicians. And on the one hand, it summarizes what we discussed before in this nice diagram form. On the other hand, I want to revisit one particular item in this diagram and zoom in on it a little bit closer, because it will give us a useful way to think about the algebraic structure that appears in this physical theory. See, one of the points that I mentioned last time is that this six-dimensional origin of this correspondence between three manifolds and physical three-dimensional theories is kind of cool, because it gives you a QFT-valued topological invariance of three manifolds. So you basically can think of it as a functor from three manifolds to quantum field theories. Problem is that this sounds crazy, in part because we don't have a mathematical definition of three-dimensional quantum field theories. So if I really had a full encompassing definition of what this QFT is, I could rephrase it in terms of, say, categories or high structures, but we're pretty far from that stage. This theory has a lot of really physical information that goes, for example, into verifying dualities, which was another topic that might be of interest to physicists. So if I were to try to extract the most algebraic structure that contains in this big package, so that's really the proper name for this theory, I would say that when we study this partition function on this 1 cross sigma, we notice something else. Not that it computes some numbers that depend on this choice of sigma, perhaps additional data, but that these numbers are encoded in the structure of modular tensor category. So what I want to do now is focus on this particular line and erase everything else, and that's going to be our algebra in the context of three manifolds, and in a second I'm going to generalize it to, or tell you an analogous story for four manifolds. So the proposal is that every three manifold defines quantum field theory, and that in turn defines a particular structure, modular tensor category, labeled by that three manifold and original choice of root system, which for us is always of type, or ton type A for N5 branes. or for corresponding 6D theory. So now, what I'll try to do in this third lecture, as I promised before, I'll try to bypass physics. If you wish, physics is good intermediate step, and it's a way to compute some things. But mathematicians can view this correspondence now as something that starts in topology, goes through black box of physics, and spits out something algebraic on the end. So that's going to be the main theme of today. So now, as I promised, for mathematicians, I'm coming back to something reasonable, tangible, but still quite interesting, that there'll be a lot of algebraic structure associated to topology. So I'm not going to describe this MTC of M3 in great detail. I may be able to do this if there are questions in the discussion session, but I'll just say a few words about what it looks like, very roughly. So if you're a mathematician, you probably care about, for example, number of simple objects in this MTC. And the set of simple objects here is pretty much the same as set of connected components of complex flat connections on a three-manifold. And if you remember, at some point, the abelian flat connections, connected components of a space of abelian connections appeared. So that was relevant to one of the lines, namely table 3 of our integrals. But this MTC actually knows a little bit more, and its Grothendieck group is, has the same rank as this number of components. So that's one property of this modular tensor category. If you want, I can give you a simple example. Say if our manifold is represented by a graph, as we discussed the other day, then MTC of this particular graph, if you, say, place -2 on all vertices, and it has a couple of edges, we discussed similar graphs before, then this is going to be MTC associated to very interesting model, so-called 3-fermion model in literature on symmetry-protected topological phases. So this is a close cousin to more familiar or small variation on so-called toric code model of Alexei Kitaev. Okay. So that's an example. And finally, if you still prefer working with numbers or concrete formulae, as we did in this table 2. So what table 2 produces for you is, given a three-manifold that calculates some partition function of this theory T of M3 on S1 cross sigma, where sigma can be, in principle, any Riemann surface. I had a very specific example in mind, but you can try to compute it more generally. And then existence of this MTC and a richer structure means, first of all, you can generalize this calculation. But second, it also means that this particular calculation can be expressed as sum over states lambda of S and T matrices that are encoding modular transformations in this modular tensor category. So in particular, here is going to be S0 lambda to the power 2 minus 2e, where S is the S matrix. So what physicists should think, if you never saw a modular tensor category before, you should think that it's some gadget that carries information about S and T matrices. And in particular, if you know S and T matrices, then you can compute partition functions on S1 cross sigma, or slightly more general fibrations of S1 over sigma. And they can be expressed as various traces on sums of matrix elements of S and T. So basically, the statement is that given a three-manifold, or in fact, more generally, any three-dimensional n equals 2 theory, there is such a modular tensor category, and it gives you S and T matrices. Yeah. That's a great question. So thank you for that. So natural question to ask is, do they have some relation to CFTs or vertex operator algebras? because MTCs often appear as representation categories of vertex operator algebras, and that's going to be our next subject. In fact, it will nicely fit into, the reason I'm emphasizing this, it will be actually used in construction at the next level. Okay, so my next goal is basically to, so if I were to say, try to attempt some mathematical definition of what this black box, physics black box is, I could capitalize on any of these computable invariants, but probably my favorite would be this one. Even though it's perhaps somewhat less studied than other ones, it behaves really nicely, and it actually fits in many different places in our discussion. Okay. So now, this being said, what we're going to do today is essentially repeat this entire story, and it's good that we had a little bit of training with the 3 manifolds, when I replace a 3 manifold by a 4 manifold. So that's going to be next obvious step. So I'm going to have the same 6-dimensional starting point, which probably is relevant for physicists, but not so much for mathematicians. I'm going to compactify that on a 4 manifold, and a simple algebra that 6 minus 4 is equal to 2 tells me that if I take out 4 dimensions out of 6 and use them for a 4 manifold, the result will be some 2-dimensional conformal field theory. And now we're actually getting in business because 2-dimensional conformal field theories do have nice mathematical definition in terms of vertex operator algebras, and we're going to be there just in a second. So here, in the previous story, topological twist along the curved manifold did eat up a lot of supersymmetry, so we ended up only with n equals 2 in 3 dimensions. Corresponding statement in 2 dimensions will be that it's 0, 2 supersymmetric conformal field theory. It's a simple calculation to see that's the supersymmetry preserved. Namely, it's non-supersymmetric, that's the 0, in the left-moving holomorphic sector, and it's n equals 2 supersymmetric in the right-moving anti-holomorphic sector. So this theory is traditionally called T of M4, or if you want to be pedantic and emphasize the root system, T of M4, G. That's a standard notation. And just as before, there are certain symmetries of cutting and gluing 4 manifolds that we're going to discuss that represent themselves as dualities of this theory, T of M4 or T of M4, G. Now, just as before, you could imagine taking various quantities or asking various questions in this framework associated to this theory, and they'll let you in very specific characteristics. But if this whole theory is topological invariant of a 4 manifold, then anything you ask about this theory should also be topological invariant of a 4 manifold, and our goal will be to see this concretely in specific examples. So one simple question I guess you can ask is, what is the central charge? So if you have a conformal theory, that's one of the obvious questions. And central charge. So question is, what kind of topological? It's a number. So if it's topological invariant, what kind of number it is? That's one obvious question. You can compute so-called elliptic genus of this 0-2 theory. It has sufficient supersymmetry to have a torus partition function. So this is partition function on T2, holomorphic partition function. And another question is, what's the resulting Q series? It depends on holomorphic part or on complex structure of these 2 torus, tau. So you can write it as a Q series, and it's going to be kind of similar to this Z hat that we saw before. And finally, you can, or perhaps not finally, but it's one of the things you can do. You can, actually, let me reserve this for analogous computation. This is a particular partition function on torus, but what conformal field theory in 2 dimensions is all about is structure of correlation functions. And you can consider analogous chiral correlators on various Riemann surfaces sigma. For example, you can consider some plane with a bunch of insertions of various operators and ask what that computes for you. Again, it should be some topological invariant. And finally, I was aiming at taking QQ homology, namely looking at a chiral ring of this theory by asking for operators which are annihilated by right-moving supercharge, but not necessarily Q-exact. So QQ homology produces something that basically wants to see it in the ground state of the right-moving sector and can be anything in the left-moving sector because this part is non-supersymmetric. So without too much anticipation, I'm going to say that this QQ homology operation, or kind of focusing on the left-moving sector, gives you vertex operator algebra because it's essentially chiral CFT, and chiral CFT is by definition a vertex operator algebra. So that's what I'm going to call VOA of M4, or again, if you want to be more pedantic, VOA of M4 comma G, but I'll assume that this G is fixed implicitly most of the time. Okay. So therefore, the goal for physicists becomes to identify this two-dimensional 0-2 theory. It's an interesting question. This theory exists. You can just start in 6 dimensions, perform this Toy-Kalatsa-Klein reduction, and ask what kind of theory do I get. That's a nice exercise. Sometimes for simple G it's easier, for more interesting G is harder. But this theory exists, regardless whether we like it or not. And then the question is, how much information can we extract? Or how much physics can we learn? So that's a good question for physicists. Yeah. They're closely related, but here typically I mean some number. So what I have in mind is that this picture for me equals really correlation function of various operators inserted at various points. So it's contained, exactly. So that's why, in fact, I was initially trying to draw one arrow, but then realized it's probably split it a little bit. Yeah, that's a good point. Yeah, so mathematically, so my focus today is going to be this object, this vertex operator algebra, VOA of M4. And again, it's a close cousin of modular tensor category that I'm going to erase in the case of 3 manifolds, and they, of course, talk to each other when 4 manifold happens to have a boundary. So the question of how the two are related will appear when 4 manifold has a boundary M3, and we already encountered such situation precisely in way of constructing manifolds from graphs. So that's going to be my universe of, say, 3 manifolds or 4 manifolds, but of course, the story is more general, so sometimes I may even venture out of it. Before I proceed describing various properties of this vertex operator algebra and perhaps even the physical theory, by physical theory, I'll always refer to T of M4, and its chiral sector will be this VOA of M4. So before I go into that, it may make sense to give a clarification on what this VOA of M4 could be for mathematicians. So from the mathematical standpoint, this compactification probably does not make too much sense unless you're really willing to think of fiber pattern. But VOA of M4 is answering a very concrete question as well in the world of math. Namely, you can try to study moduli spaces of instantons for group G on your 4 manifold M4 and take its cohomology and ask what kind of algebraic structure acts on this space. So let me denote the space by V. So this is going to be some vector space V, and if I have arbitrary instanton number, it's humongous. It's an infinite dimensional space, and I can ask what kind of algebraic structure is acting on the space? That's a reasonable question. Mathematicians, in fact, have asked this question. And Nakajima answered this question in 1994 when he considered four manifold of the following type. It's a linear graph in our notation with all the labels being -2. Okay. So such manifold is sometimes called A sub n minus 1 if there are, let's see, n minus 1 vertices. And then corresponding answer was that in this case, VOA of this manifold A sub n minus 1 is actually a Poincare algebra of type SL little n at level capital N. Okay. So this was a prototypical example for many later attempts, including AGT correspondence, which gives an answer for, so AGT is another classical example for manifold, which is basically R4, but R4 viewed equivariantly, just like in this vortex partition function that I was writing in the case of three manifolds. Capital N is still on the board. That N, yeah, that N. Right. So therefore, what this VOA from 4 trying to get at is answer the question, what algebraic structure acts on instanton moduli spaces? And that's in general pretty hard to answer, in part because these moduli spaces are horrible. In particular, if you really take it at the face value, they're actually very sensitive to the metric. So you expect something topological, but this space is extremely sensitive to the metric. You can, yes? Correct, yes. It's basically LE space or better resolution of AD type singularity of type A. So then you can slightly improve the situation by trying to invent a slightly better moduli space. For example, if you think about this problem, and in particular the Torus partition function and this whole setup, you may think that Vafa-Witten moduli space, which is space of solutions to Vafa-Witten equations, is going to be a better candidate. But even that is not ideal. It slightly improved the situation, but it's not perfect. And again, there are several iterations. I can tell you the final answer to which you to which problem you can associate this VOA from 4. Morally, what it's trying to do, it's trying to make sense of this statement, and that's where this point of view of first compactifying on a 4 manifold, analyzing this two-dimensional theory, can actually help in mathematics to properly resolve singularities and compactify something that's hard to analyze from the analysis viewpoint. And if I have time, I'll give you a couple of examples of that. So that's the mathematical question. So there are two questions that this VOA from 4 is trying to answer. Physical question is, what is the chiral sector of compactification? And the other one is, what is the algebraic structure that acts on moduli spaces of instanton? Right. So why the two are the same? That's actually a very good question. The two are the same because of the following. So if you consider this theory of 5 branes on T2 cross 4 manifold, and consider two different reductions. First, say, on a 4 manifold, then you get a two-dimensional theory, which is our friend T of M4, on a 2 manifold, on T2. Okay? Alternatively, so you're actually in a situation which aims to compute this elliptic genus. You're actually here. So here I can start filling the slot. You're computing chi of Q, the character of that VOA. If you do the other reduction, first compactifying on T2, what happens is that you reduce on T2 first. What you get is 4D n equals 4 superrank mills. This is on a 4 manifold on M4. But now, in order to be defined on a curved space, this theory has to be topologically twisted. And if you think what it is, it's actually Vafa-Witten twist of n equals 4 superrank mills. And therefore, you get a statement that this character of this VOA of M4 is nothing but Vafa-Witten partition function of M4. Okay? So what the statement about the cohomology is trying to ask for categorification, namely this chi is basically the graded trace, graded by instanton number, and from the viewpoint of VOA, it's graded by L0, the stress energy tensor or conformal dimension eigenvalues. And relation between this equality of character and Vafa-Witten partition function and the VOA and this big module is that it's basically trying to categorify or replace numbers by vector spaces and lift the statement about algebra that acts on this module. So there are a couple of things I can, in fact, thanks to a question, immediately try to address here. So first of all, I can replace this 2 torus by any sigma and get some theory of class S on one side, topologically twisted, and here it will be some chiral partition function of a 2-dimensional theory on sigma. If we do the following, just like in this previous discussion, what's happening here is that from the viewpoint of 4 manifold, this theory is fully topological. We use supersymmetry to perform full topological twist, but along sigma we have some holomorphic twist, also sometimes called half twist in the language of 2-dimensional sigma models with 0-2 supersymmetry. And remember, I told you before that the 6-dimensional story does not admit full 6-dimensional twist, and what's written on the board here is really the strongest you can hope for. So it's fully topological in 4 dimensions, but it's only holomorphic in the remaining 2. And that's the best you can get. You cannot get rid of z-dependence, holomorphic dependence in 2 dimensions, but in some sense that's pretty cool. It's good that it's precisely where this chiral or holomorphic structure encoded by VOA correlators is going to be useful for us. So it's going to be pretty rich structure. And another generalization I can and should probably make immediately is that, like here, I mentioned that in general it's natural to consider 4 manifolds bounded by 3 manifolds, and if so, you should pick some boundary conditions. And the natural choice of boundary conditions for Vafa-Witten theory is precisely a choice of complex flat connection on a 3-manifold MP, and that's where this MTC and our previous discussion will come in very handy. And this label rho will basically appear everywhere. So if you study, say, moduli spaces, you have to specify the boundary condition rho. And therefore, what you get is not just a single infinite dimensional vector space, but a set of them labeled by rho. And this will be various modules of VOA of M4, and corresponding characters will be Vafa-Witten partition functions on a 4-manifold with boundary and suitable boundary condition. Okay, any questions? So there are several pieces of information that are usually available pretty much on any four manifold that can help us if we don't have any other way to get this theory, two-dimensional theory, corresponding vertex algebra. There are at least three useful tools that you can keep in mind. One is central charge, which is extremely helpful. We're going to discuss it in a second. And if we're aiming to get some chiral CFT or two-dimensional full CFT with left and right sector, that's a basic information that we want to have. We want to know, roughly speaking, what's the central charge. That's a basic characterization. Slightly more useful information, in case if a manifold has boundary, is this modular tensor category for the boundary. Because if it happens that four-manifold is bounded by M3, then this will always be a subcategory in a representation category of this VOA of M4. And therefore, if you know something about this, it gives you a little bit of a constraint about VOA or modulus of M4. That's also information that's fairly computable. And in the increasing degree of complexity, if you happen to know Vafa-Witten partition function of your theory, perhaps, again, if you have boundary conditions with boundary conditions, then it gives you information about characters, not just how many modules you have or how they behave, but real characters. But unfortunately, this is really hard to compute, so I listed it in an increasing degree of complexity. The computation of Vafa-Witten partition function is currently available only on complex surfaces, and interesting questions about four manifolds are way outside of Keller surfaces where this is typically done. So, but there is ongoing work by many people, including, say, Gadde, Toda, and Richard Thomas, and various others, of trying to compute the Vafa-Witten partition function for many manifolds. They do run into exactly the same issues of how to compactify moduli spaces, what really to take as a definition. It's a very challenging problem, whose glimpse we may see today. But in fact, sometimes they even get different answers for Keller surfaces, but that's precisely what physics, perhaps this alternative route via first getting the algebra, may be very helpful. Yeah. This is what? If you want me to, so yeah, it's a separate discussion. I ventured into it a little bit, so I'm not going to say more now, but I'm happy to discuss it in the discussion section. It will take quite a bit to formulate it, and yeah. But it's in the paper, so you can also look up there. Okay, so I'll actually go to now simpler things, and first try to address question of, for example, what's the central charge of? So that was one of the first items. So I'll try to tell you first what the central charge of this VOA is. By the way, perhaps I should, before I proceed, I should also say that just to give complete table, I tell you kind of yeah, I already said what the character of the modules for this VOA gives. It gives Vafa-Witten partition function. Central charge we'll discuss in a second. It has to be some topological invariant of a four manifold, but I'll say here that correlators of a particular type, there are many of them, but certain of them, encode Seiberg-Witten and Donaldson invariants of M4 of a four-manifold. And the reason I say this is because just to make sure that this VOA is not entirely boring and trivial, because it could have been that it's an invariant, just like many other things we discussed, but it's very uninteresting. This is not the case. You can recover Donaldson and Seiberg-Witten invariant as correlators in this VOA, so it's more interesting because it contains all this information and probably something else. And once I am at it, I should probably say why this is interesting to four-manifold people. Because four-manifolds, unlike three-manifolds, are not classified. And we're talking about the smooth ones. So we don't know complete or actually good invariance of manifolds. So one particular operation that illustrates how bad the situation is, and current situation really is based on this Seiberg-Witten and Donaldson invariants. They're equivalent conjecturally, and everything else that people studied boils down to Seiberg-Witten invariants, unfortunately, so that's all we have. But see, the problem is, and it's very easy to see where this problem comes from, if you take two four-manifolds, M4, say, plus, and M4 minus, these are closed four-manifolds. Take your favorite, K3 surface would do. Ask that B2 plus of each one of them, M4 plus minus, is bigger than 1. So K3 surface indeed is a good candidate, or anything else you like, Harikawa surface if you wish. Consider connected sum of these four manifolds. That's a basic operation which does the following. It takes a little ball from each one of them. So if you have one, M4 plus, and another one, M4 minus, then remove a small ball from each one. It creates a boundary, which is a three-sphere, and reglue it back. So that's operation, very simple to visualize, called connected sum. Theorem, which actually goes back and is in the original work of Donaldson, is that Donaldson invariants for such connected sum vanish, and there is a simple analogous theorem that says Seiberg-Witten invariants vanish. So therefore, our most powerful invariants on the market are completely blind to the most trivial operation on four manifolds. So that's how desperate we are to find something new. So analogous statement in the context of this VOA is going to be that VOA of connected sum is simply a tensor product. It's the simplest operation on vertex algebras that you could possibly imagine. So VOA, if you apply it to the same procedure of M4 plus connected sum M4 minus, is going to be basically VOA of M4 plus tensored with VOA vertex algebra of M4 minus. And that's not only natural, but it comes from the fact it's actually easy to trace to these moduli spaces, because here the vanishing comes from a very stupid reason. So you have moduli spaces of, say, instantons or whatever their proper replacement on both components. And when you take this connected sum, there is in moduli space a certain circle that basically kills you when you try to take a characteristic, when you try to compute the number. So the spaces actually are quite rich when you take the connected sum. But when you try to compute the number, that's what gives 0. So the point here is to try to categorify it, or rather work with something, with vector spaces or homologies, rather than numbers. And that's precisely what this thing is trying to achieve. Okay. So that's why this is interesting. That's why this is also why we have limitation in terms of Seiberg-Witten and Donaldson invariants. But now I'll go back and try to, again, describe for you some properties of this theory and corresponding vertex operator. Any questions? So physics actually is very useful. Namely, this route of physics is useful because it quickly gives you a way to determine central charge from the corresponding conformal anomaly in 6 dimensions. So central charges controlled by anomalies, which do integrate over the fiber, just like usual characteristic classes. And that allows you to determine the values of C left and C right. There are, in principle, different central charges. And if you want a sample of how it looks like for G, which is SU2, and like everything in my lectures is going to be limited to rank 1, here is the table. I'll give you simple examples of 4 manifolds and corresponding values of C left and C right. So C left is going to be the actual central charge of VOA FM4. It's, so this vertex algebra is describing the chiral sector, and C right is going to be the central charge of the right moving part, which is not visible directly to VOA FM4. So, for example, for a 4 sphere, one of the simplest 4 manifolds, you get here 26 and 27, which you can write suggestively as 2 plus 24 and 3 plus 24. Okay. For CP2, you get pretty large number, 57 and 60. And if this is your first time seeing these numbers, you think that that's probably crazy. It's a conformal theory with very large central charge. So what's good about it? But there is actually a lot of things which are good about it. So for completeness, if I mention CP2, and I have to be fair to everybody, I have to give you the one for reverse orientation, CP2 bar. And here the values are quite different, 21 and 21. So what's going on? We just reversed orientation, suddenly things change a bit. So S2 cross S2 gives you 52 and 54. If you want to consider a more general connected sum, the operation that I just explained a moment ago of m copies of CP2 and, say, n copies of CP2 bar, then the answer will be 26 plus 31m minus 5n. And here it will be similarly 27 plus 33m minus 6n. Okay. So all of these formulas and computations are really easy. They follow very straightforwardly from the fact that we define this theory as a reduction of something on a 4 manifold. And finally, if you work with, say, S2 cross some Riemann surface of genus G with n punctures, the answer is going to be 2G plus 4n plus 1, and here 6n plus 1. So these are some sample of examples, just to show you how easy and how concrete it can be. Right. So I have to point out that actually general formula that you use to compute these values of central charges actually works best if your manifold, 4 manifold, is generic. Generic means that metric is arbitrarily crazy and does not admit, I mean, the same topology does not admit a metric with a reduced holonomy. Because when reduced holonomy is possible on a given manifold, this calculation actually is not reliable. And in fact, this last item here, this one, is not obtained using general formula. So here it's crucial that this manifold is scalar. So holonomy is reduced, and there is something subtle going on. So such subtleties, I want to warn you, are present when holonomy is reduced. So even though some of my other examples are also scalar, actually everything is fine. So for everything else, the formula can be applied, and you can go through and get your central charges. For K3, it's 24 and 12. Exactly, yeah. That comes from accidental flavor symmetries. So, yes, some mixing, exactly. So if everything is generic, in other words, if in garden variety 0, 2, everything is fine. But as you know very well from this mixing, for example, here, even the supersymmetry is enhanced to 0, 4. And that's Yeah, there is more going on. So I want to warn you that if metric is scalar, which is usually nice, like I said, it's actually good for Thomas, Lotter-Gotchi, and others to do computations of Waffle-Witten partition functions. That are precisely the cases where they can do calculations because of the Keller structure. Here, in the computation of central chart, this is actually the subtle case. And if you're on a generic manifold, such as this connected sum, everything's fine. Exactly, exactly. So modularity of Waffle-Witten partition function is precisely modularity of characters of this VOA FM4 from this point of view. Okay, so, right. So therefore, what are these central charges? So I gave you the answer for SU2. And this general method, which is based on anomalies, basically gives you a formula, a very concrete formula again, which works generically. For instance, left-moving central charge, which is really relevant to vertex operator algebra, in general can be expressed as 13 chi plus 18 sigma. And you can indeed verify that most of my entries in this table feed this general formula precisely when this special delicate phenomena don't happen. So I promised you that every quantity in this two-dimensional conformal field theory is going to be a topological invariant of a four-manifold. So sure, Euler characteristic and signature are good invariants of a four-manifold, but they're quite classical. This is not very surprising, though, because you do expect that central charges C left and C right are basic quantities that characterize theory, and Euler characteristic and signature are indeed basic quantities or topological invariants that characterize four-manifold, so it's nice that they sort of match together. Okay, any questions? Okay, so now I could proceed in several different routes, and I could, first of all, try to describe various properties of this vertex algebra and say some facts about it, such as, again, that character is equal to a Witten partition function, which I did. I could also try to give you construction of this two-dimensional theory or corresponding vertex algebra in various classes where it's known. So that could be construction part of the talk. And then, as we already learned in previous cases, these constructions usually have some kind of relation, such as Rademacher moves that Piotr talked about. And they should be represented by equivalences, equivalences of either the full two-dimensional theory, which has right and left sector, or just left-moving chiral algebra VOA FM4. So I could talk about equivalences. And I probably won't have time for everything, so instead what I'm going to do, I'll basically give you a little sample or say a few words about each topic, so it will be more like a survey or appetizer or sampler plate. But again, if there are specific questions, I'll be happy to address them in a discussion session. Good. So construction and equivalences usually come from gluing of various basic pieces of four-manifold, just like you can glue various basic pieces of three-manifolds. So first I want to tell you how the story relates to what we already learned in the previous lecture. So suppose you have a four-manifold, which is big and contains two pieces, M4 plus and M4 minus, just like in the connected sum operation, except that here I take the general slice to be some M3, not just necessarily a three-sphere, although three-sphere is a perfectly legitimate example. And suppose I want to reduce this picture to two dimensions to obtain T of M4. So how do I do this? Imagine stretching this operation or gluing operation into long sausage such that in the middle we see M3 cross a real line. And we already talked what happens when you compactify from 6 dimensions on a 3-manifold. You get a 3-dimensional n equals 2 theory called T of M3, again, for that same choice of root system that, that specifies the whole picture. So you get such a theory on a real line. So real line for me is going to be this direction. It's the direction of the sausage. And again, the counting is simply that 6 minus 3 is still 3. But now, this, when we try to approach the end or go in this direction, as you can see, we can go only that far to the left and only that far to the right, because this geometry is kept off. So what's happening is that as you approach this, this boundary here, this dimension basically stops, and the information about M4 minus is encoded in a boundary condition which we can naturally call T of M4 minus in this case, and T of M4 plus on the other side. And it's a simple calculation to see that just like the whole complete two-dimensional theory that we want to study, they preserve two-dimensional 0-2 supersymmetry. And the entire theory for closed manifold, which is built out of 2 pieces glued along 3-manifold, is now represented as a 3-dimensional theory sandwiched by 2 boundary conditions. So this boundary condition and this boundary condition, so that instead of 3-dimensional translation invariance, it only has 2-dimensional translation invariance along the boundaries. And this direction is broken, so it's 3D theory lives on interval cross R2, or interval cross sigma if I am to keep sigma as part of my notations. Okay. So in this way, first of all, MTC naturally gets in the game. And secondly, if you ask now, how does computation of the elliptic genus in this two-dimensional 0-2 theory comes about, it has connects very naturally to this index of coupled two-dimensional, three-dimensional system that I mentioned yesterday. We actually used it in the computation of this invariant z hat from the 3D point of view. So now it applies to the system of 3D n equals 2 theory with a 2D boundary condition labeled by 4-manifold. Yeah. That's in some sense Abhijit's dream to describe it that way, but in principle, I mean, this M4 plus and M4 minus, they there are 2 manifolds bounded by the same 3-manifold. So a priori, I don't want to use any more. Yeah. Yes. So therefore, what this M4 minus does, it actually defines a boundary condition in a theory which is 1 dimension higher. So what happens is that there is a swap in dimensions. So if you compactify on high dimensional manifold, less dimensions you have left. So that's why it defines a boundary condition. And by itself, this one is not really a well-defined theory. So it's only a relative kind of theory which can be coupled to a theory in 1 dimension higher. So that's the nature of it. Perhaps I should also mention that in literature on vertex algebras, if there are any experts in the audience, what's really called VOA is usually vertex algebra which doesn't have any fermions. And this story, of course, always does. So this is always, first of all, super VOA. Also, sometimes in vertex operator algebra literature, you want to emphasize that you have a stress energy tensor by saying conformal VOA. That's yet another adjective. I don't want to use any of these adjectives. Another name for this conformal or non-conformal VOA would be just chiral algebra. So I'm encompassing all of them into VOA, which is also pretty standard. But again, not everybody uses it. So that means that same four-manifold can be sliced and built out of different sandwiches. Different sandwiches of 3D n equals 2 theories with different sets of boundary conditions. So this is exactly this kind of equivalence that if I had time, you would be verifying that indeed you have same geometry or topology, and you cut it in many different ways, and it gives you a different description. So that's actually the origin of some of the equivalences, which, again, I probably won't really be explaining. So this is an example of gluing. And then you can have analogous story if you have, for example, reverse role of 4-manifold and 3-manifold. Namely, you can consider 2 3-manifolds and a cobordism between them. That's also a natural building block. So then, by analogous translation, you would quickly learn that it corresponds to some interface or domain wall between two 3-dimensional n equals 2 theories associated to 3 manifolds that are related by the cobordism. Okay. So now I'm going to give you another example and switch subject a little bit, just again for balance to give you kind of survey. Sometimes if I give this kind of talk to topologists, which are really hardcore topologists, which say, yes, we know that Cyber-Quitten and Donaldson and invariants vanish under connected sum, but we still love them, and can you give us something like that? Why do we have to learn all this algebra? So here on the board, I still have topology, physics, and algebra. What I love about the story is that they talk to each other. There is a lot of point of contact, interaction, and it's these bridges which I find extremely exciting. So to those people, my first response would be, you're making a huge mistake. If you focus on, say, topology and don't want to learn algebra, they say it's too complicated, I don't want categories, or I have no idea what vertex algebra is. So I actually devised to them another response, which I'm going to give you in a second, that even if you don't care, if you really want to study PDEs and do all traditional topology, this vertex algebra will pop out to you whether you want it or not. So it's like, again, this T of M4, it's a fact of life. You can love it, you can hate it, but, or you can study it, but it's there, regardless of whether you love or hate it. So therefore, what I'm going to do next is I'm going to start with the topology problem, and we'll see that VOA emerges kind of automatically. And again, I'm not going to give you all the full details, but I'll sketch hopefully enough that you can see what's going on. And my point will be that it works for general 4-manifold, so in this case, there will be no assumption of 4-manifold. It will be taking absolutely generic, so that we don't use any special crutches of Keller geometry or complex geometry. So let's see, we talked about central charges. We talked about gluing a little bit. Now let's talk about going from topology to algebra. And typical starting point for topology, as I already mentioned several times, is some set of PDEs. So imagine that you have Cyber-Quitten equations, which in 4 dimensions look like this. You have gauge field A, spinor psi, section of spin bundle. So A is a connection on line bundle. And let's call it L, and psi is a section of spinor bundle tensored, say, with L. And the two equations that people usually write, or that Cyber-Quitten write, are the following. You have equation that self-dual part of A is square of the spinor, moment map, if you wish, and the Dirac equation for the spinor psi. Okay? So if you have such system, then what you usually do, you construct the moduli space of solutions to these equations. It depends, of course, on the choice of a four-manifold M4, but it also depends on choice of topological class of our bundle. So if lambda denotes first Chern class of our line bundle L, then it will also depend on lambda. So lambda lives in H2 of M4 with integer coefficients. In fact, it's a choice analogous to the choice, what we call B, in the story with three manifolds. So the Cyber-Quitten invariant are labeled by something, and that's what they're labeled by in 4 dimensions, and you saw what they're labeled by in 3 dimensions. So one constructs this moduli space of solutions. It's convenient to... yeah, so it's... yes, thank you. Oh, compare with. Use of B in our previous story. So lambda, in fact, I maybe should have called it B, but I'm sure I'll forget because this is fairly standard. So then what you do, you take integral of first Chern class of some universal bundle to half dimension of the space. It doesn't matter. It's some characteristic class, top degree characteristic class on this moduli space, and you get a number. So this number you call Cyber-Quitten invariant now of a 4-manifold that depends on lambda, and that's exactly analog of what I told you how to compute in practice in the very first lecture. But for 4-manifold of the form S1 cross M3. And by the way, everything we said about 3 manifolds before now can be used very efficiently. If you take 4-manifold to be S1 cross M3, you can basically repurpose our previous discussion and learn immediately the corresponding VOA and so on and so forth. But so this is a standard problem, and this moduli space, what makes it very special compared to, say, Vafa-Witten problem or any other problem that you can imagine, there was no better candidate invented yet, that this moduli space is compact. And for generic choice of metric on M4, it's actually nice and compact moduli space. It consists of points, in fact, if it's non-trivial. So that's what makes a Cyber-Quitten system special. And for any other problem in gauge theory that people encountered so far, be it Donaldson theory, Vafa-Witten theory, or anything else, moduli spaces are non-compact and badly singular. And we're going to make our story here very complicated in just a second. To make that, what I'm going to do, I'll say that I have not just a single spinor psi, but n copies of them. So I runs from 1 up to n, or rather nf, because n is already reserved. It was used for a number of phi branes. So not to confuse it with that, I'll call this n sub f. And physicists have another reason to do that. So then I have to impose Dirac equation for each of these spinors and consider now this kind of system. I'm still going to keep U1 line bundle. But the problem is that now this moduli space of F monopoles, so-called multi-monopole Cyber-Quitten problem, is completely intractable. It has been studied. This is the simpler system than Vafa-Witten equations or anything you can imagine. But even though it has been studied by Bryant, Wentworth, Haidit, and Lopusky, and many others, in fact, even Simon Donaldson, this is hard. The reason is that this moduli space here, this M sub NF of a 4-manifold with lambda, the way it looks like a cone on something with horrible bad singularities of a very sticky nature here in the origin, and, if you wish, various other branches coming out of those singularities. So it's singular, stacky, non-compact. How do you define the integral? There is no much help from complex geometry in general, unless you make assumptions on the choice of 4 manifold, and that's being the difficulty. Nevertheless, this problem has an obvious symmetry, and now in the present day, especially the kind of games that we play in physics, suggests an obvious solution. So the way these equations are set up, they're completely invariant under permutation, or in fact any rotation of this spinner's psi. So therefore, what happens is that there is an action of SUNF symmetry in this problem, which descends to the action of SUNF in the moduli space. So therefore, even though this moduli space is non-compact, one obvious thing to do if you have this structure is to use it. Namely, to consider not the usual integral, which was useful in the case of Seiberg-Witten invariance, but now equivariant, namely SUNF equivariant version of the integral. It will depend now not only on choice of 4 manifold and topological class lambda, but it will depend, in addition, on equivariant parameters for this SUNF. So if I call Z1 and so on, Z and sub F, equivariant parameters, as usual, they live in Lie algebra of the Cartan of our group, which is SUNF. Then we may have a hope to get something sensible if, and that's a big if, the fixed point of this SUNF action are compact. So then we can reduce everything to the usual integral, apply a T-blot localization, and extract the answer. Okay, so that's a sensible problem. Even though this moduli space is non-compact, and again, I can tell you a lot more about geometry and asymptotic behavior, it's actually easy to control. Our goal will be to ask, what are the fixed points, and can this integral really be taken or made sense of? And the answer turns out to be yes. So the fixed points, SUNF fixed points, correspond to disjoint union over I running from 1 up to an F of single monopole, the usual Seiberg-Witten moduli spaces of the type M4 lambda, and as we discussed a moment ago, they are compact. There are quite a few of them. Namely, if you have an F, say 50, then there'll be 50 copies of pretty much the same thing, but they sit inside the moduli space of, so they're contained in this big moduli space of multi-monopole problem. And now, because they're compact, you can actually define this integral, you can make sense of it. So I'll say that SUNF equivariant integral, so this is a theorem that, based on work with Pavel Putrov and Koля Dedushenko, that this SUNF equivariant integral over M and F of M4, or rather M4 lambda, with a suitable top characteristic class. First of all, it boils down to Seiberg-Witten invariance. So it knows about Seiberg-Witten invariance, and that simply has to do with the fact that fixed point components are precisely the usual single monopole solutions to these PDEs. So there is a prefactor here, Seiberg-Witten of lambda, but then, most interestingly, we have the structure of a typical chiral correlator of NF points on a plane. So sigma here is a punctured plane, and you can consider points Z1, Z2, Z3, and so on, Z and F. Okay. And even though previously, in the setup of the problem, the Z's had no real meaning, they were just boring equivariant parameters who lived in the Lie algebra of the Cartan, of the group that we're trying to localize with respect to. Even though they started life as something boring, now if you interpret them as positions of the points on the plane sigma, what happens is that your result takes form of chiral correlator in the vertex separator algebra, precisely that you would find from this compactification of this theory on a four manifold from 6 dimensions, and the answer has the following form. It's 1 over product over j not equal to I in the denominator, zj minus zi to the power 1/8 lambda square minus sigma, where lambda is our 2 class, the first term class of the bundle. Sigma is a signature of the four manifold. You may recognize here the index of the Dirac operator twisted by line bundle L. And this is nothing but correlation function of various operators. We call them S for impurity, inserted in points Z1 through Z and F. In this algebra, chiral algebra VOA of M4. Okay? So if I had more time, I would actually derive for you this VOA of M4. It's not too hard. And you could compute this chiral correlator and see that it's perfectly consistent, just as promised. But what's cool is that once you have this VOA of M4, once you have this vertex algebra, you can compute its elliptic genus. And of course, it will give you Vafa-Witten partition function. So the point is that this VOA unifies many different gauge theoretic problems, even if you didn't care about them. So therefore, this is a natural way to argue that topologists should learn, or again, the structure is present in some of their answers, whether they like it or not. And if I had more time, what I would do, I would basically talk to you about equivalences. So that could be another subject of this vertex operator algebras, and derive a lesson in the opposite direction, that even if you didn't care about topology as an algebraic type of person, people who study vertex algebra say, I have no clue what Kirby calculus are, why should I learn them? The point is that if you study equivalences in vertex operator algebras, they would reproduce, just like we saw this coming out of calculus in the basic integrals in lecture 1, that Kirby moves emerge and nicely describe various equivalences. But again, that's another topic which I leave for some future occasion. Thank you.
So to understand what is understood here as a topological invariant, when you write T of M4, it is a theory which is independent of any decomposition of the manifold and so forth, or it is a class of, equivalence class of theories?
Yeah, physical theory is defined as superconformal theory in the deep infrared upon compactification from 6 dimensions on a 4 manifold, and if it's really topological, you should think of it as taking the metric such that four manifold is tiny, very small, so you force the flow across the dimensions from 6 to 2.
But it does not involve any markings or decomposition of M4.
If B2 plus is greater than 1, then no.
So these which were equivalent parameters, how are they to be interpreted as positions of insertion points?
Well, there are the correlation function that you compute in this chiral CFT involves particular operators inserted, operators that are present in this VOA, inserted at point Z1 and so on and so forth, Z1 through Zn.
But is there a way to see it from this brain picture?
Which picture?
I mean, this M5 brain picture.
Oh, from the M5 brain picture, basically, yes. What I'm describing is the sigma is nothing but the Seiberg-Witten curve, actually. But the Seiberg-Witten curve for a problem which has U1 vector multiplet and NF hypers of charge plus 1. So these positions, Z1, Z2, Z3, and so on, are singularities on the U-plane. So this picture is basically the U-plane. And in the case of NF monopoles, there are NF special points. And that's quite clear that it's something like that should work, because on the one hand, as I described in the beginning, you could do holomorphic twist, compactifying fibrane theory on sigma Seiberg-Witten and get Seiberg-Witten theory on a four-manifold. But now I'm basically reversing it and asking for analogous structure to commute.
Thank you.
I had probably a dumb question to ask, but when you talk about gluing, is there a way, for example, like instead of slicing off an 4 with a single M3, which separates it into an M4 minus and an M4 plus, can one consider like an infinite family of M3s, which kind of runs along the so-called sausage direction? So you don't have to worry about any M4s as boundary conditions, and you just work with M3s?
That's a good question. I don't know much about it, so I think all kinds of gluing are interesting. So I am certainly not an expert on all of them, and sounds like an interesting possibility.
Actually, I was a bit confused by your description of sigma. Isn't it part of the six-dimensional space-time? How can it be the U-plane?
Well, here it basically emerges. So here it's emergent geometry from a topology problem. But if you think about it in terms of this T of M4, claim is that indeed you take six-dimensional space-time to be M4 cross the sigma, and you can view it both ways, either compactify on sigma first, if you wish, or do the opposite. So here what I try to do is to, without any knowledge about 6 dimensions, which explains why this works, to hard-boil skeptics in topology, start with their traditional problem of moduli spaces and basically see that localization forces. So the coolest structure about VOA is this chiral correlator. So that's basically what's coming out of this localization computation. Well, that's basically U-plane emerging for this multi-monopole problem. Oh yeah, yes. So here so in this case of rank 1, there is a one-sheeted cover of Seiberg-Witten curve over U-plane. Yeah.
So how much do you actually learn about these VOAs? I mean, their structure, classification, things like that?
So my collaborator, Boris Fagin, has this dream that the world of vertex algebras, meaning chiral algebras, not necessarily conformal and super algebras, is so wild that it may match how wild the world of smooth structures and four manifolds are, or at least roughly they're of the same complexity. I'm not sure how they should be matched. But then it's a good question to actually construct such VOAs for different four manifolds and vice versa. So if you have your favorite four manifold, you can ask what's the corresponding VOA. If you have your favorite VOA, such as Ising model, you can ask what's the corresponding four manifold. And both directions are extremely interesting. So you actually do learn something highly non-trivial about, say, equivalences. For instance, even in first pioneering steps with Abhijit and Pavel, we had this triality, which relates three different looking VOAs, which are actually the same, or three different, in fact, physical theories. And that came about by looking at what's called Handel slide. That's a non-trivial Kirby move and four manifolds version. So in the first lecture, I emphasized that I'm really looking for new dualities. So luckily, the topology led us to new dualities, both in 3 dimensions and 2 dimensions. So you do learn equivalences.
And there were, like in last couple of years or so, those papers by Gayota as well. They also look at VOAs in some brain systems. Is there some overlap or intersection with what you are doing?
Yeah, there is a connection in case of toric four manifolds. So if your four manifold is toric, it can be encoded by simple diagram like this, for example. And then this does overlap with their construction. So in this case, I didn't talk about how you do this gluing. In general, it's done either by extensions or BRST reductions. In this particular setup, it would be by extensions. So you can actually, closer connection is to work of Rabchak and Prochaska. So they build various vertex algebras from webs. And if you take the web to be the toric skeleton of a four manifold, then it's really the same. So that's one overlap. There is also an interesting overlap with chiral algebras of Beam and Rastelli. If you take, so that's another type of example. You take four manifold to be S2 cross a Riemann surface, say with simple punctures or non-punctures, then it just happens that chiral algebra that they get for class S in their story is exactly the same as this VOA of M4 for this four manifold. And that's kind of interesting because the physical setup is slightly different. So Beam and Rastelli don't have a two-sphere. But there is a very nice paper by Van Binyan, Pavel Putrov, and I'm forgetting some other author, who analyzed VOA of M4 for this theory. And they actually they actually studied full two-dimensional theory, not just VOA, but the full T of M4. And chiral sector of this guy happens to be the same as chiral algebra of Beam and Rastelli. So there are interesting overlaps in special cases where four manifold has a Riemann surface. So what do you mean? Yeah. So different four manifold gives rise to different VOA. So I'm saying take Riemann surface that determines class S, tensor it with S2, compute VOA from 4. It's going to be the same as Beam and Rastelli for class S labeled by G and sigma. That's the statement, and it's a true statement. I don't think so. I try to think about it. I don't fully understand that because I think, so physical systems are not related. For example, chiral sectors are exactly the same for Beam Rastelli and for Pavel and Van Bien and anyway. But Rastelli, of course, don't have the right moving sector. So they don't have the CFT, whereas Pavel and company do. So, and moreover, in 6 dimensions, Pavel and company have a two-sphere, whereas Beam and company have some kind of omega background of a very strange type. So what's happening in some senses, for some reason, BPS sectors with that omega background or topologically twisted S2 happen to be the same. I think that's the closest statement I can make to truth, but I don't understand that. So that's an interesting, Piotr asked me about overlaps, and I thought I should be fair to everybody.
Non-unitary.
Yes.
In general, but here, as it's following from a physical theory, it should just be a unitary with positive central charges and so on.
Not necessarily. Not necessarily. I was going to mention this. It's a curious topic. It's actually a fun topic, because if you go back to the table I gave you of central charges, at some point, all of them were positive, which didn't alarm anybody. But then at some line, I said, let's take general number of connected sum of CP2 and CP2 bar. And then that formula minus sign appeared.
But what about this?
So here
be okay.
in the theory, it quite often happens that, in fact, central charges may be negative, but that doesn't alarm anybody. Or so there is interesting.
Sorry, I mean, if you first compactify on sigma, you get a nice 4D theory class S, and then you compactify on S2, still
Right.
should be nice. I mean, just to kick
So
it.
let me try to clarify. So what happens is that all of these theories have something non-compact. They don't have normalizable vacuum. And another thing is that sometimes, often you get nice-looking VOA, but with a slightly redefined stress-energy tensor. That's a really interesting point. Like I said, I was even thinking of mentioning it. And as a result, it shifts. It's a nice-looking algebra. Everything is fine, but it shifts central charge. And in particular, that's the relation between beam Rostelli VOA versus Pavel and Company VOA. It's the same algebra, just stress-energy tensor is shifted a little bit by something very boring. And again, the same phenomenon actually appeared when I was mentioning disconnected sums. So there were minus signs. Right. So that's probably also related to the fact that I don't see direct physics duality. But again, I'm mentioning this just as a curious point that the algebras are closely related. And I think it's interesting that groups never cross-reference each other. I don't think they noticed. I asked both members. I think they're all friendly, and it's not because they hate each other. They just didn't know. So. But I agree, it's a good question, and somebody should elaborate. And the reason I emphasize it, I think that's a good project to study the precise connection. Maybe localization or something like that.
But let's thank Sergei again for a wonderful course.